Hello, everyone, and welcome to this new appointment of the 40 Under 40 lecture series on combustion. Today, we have the pleasure to welcome Dr. Khushboo Pandey from the School of Engineering at the University of Edinburgh. She has completed her Master of Science and PhD from the Interdisciplinary Center for Energy Research, the Indian Institute of Science. She was later a postdoctoral researcher at the Combustion Acoustics and Flow Physics Lab at the ETH Zurich in Switzerland. And in Edinburgh, she's now heading the Experimental Multiphysics and Multiphase Flow Group. And her focus is really on multiphysics and multiphase flows to establish clean and low emission combustion and sustainable aviation fuels. A very recent news is that she recently received the EPSRC New Investigator Award. So congratulations for that. And today she will discuss the lean azimuthal flame combustor concept for ultra-low NOx and emission-free aeroengine propulsion. So thanks again for having accepted our invitation, and I give you the word for your presentation.
Thank you, Alessandro, for the very kind introduction. Hello, everyone. So as Alessandro presented and said that I'm going to be talking about lean azimuthal flame combustor concept for ultra-low NOx and emission-free aeroengine propulsion. So starting with a very dire image. My slides are not moving, is it?
Not, I don't see them moving, yes, at the moment.
Okay. So, yes. So starting with a very dire image of burning issue of climate change, we know that given the extent of emissions from different industries and our domestic use is resulting in environmental challenges, and that results to various everyday problems that we are facing, like increasing of temperature, increasing in environmental issues. And to coming back to what we have from our side, that is aviation, if we look at the CO2 emissions from the aviation, we see that from 2000 onwards, the CO2 emissions from aviation has continuously increased. It took a dip when it was when we faced the pandemic. However, since then we are again going back up quite fast, and which is a bit dire to see that the curve is quite steep, and we have reached exactly 90% of the initial increase in CO2 emissions. Recently, if we look at with our net zero emissions scenarios, if we stop here and then we look at how to achieve net zero scenario by burning biofuels, sustainable aviation fuels, and we keep on this trend, so hopefully we can achieve the targets of 2030 of going with net zero scenario. So specifically for the aviation industry, how do we do that? So it requires a lot of technological development. And as we know, sustainable aviation fuels is one of the goals to achieve sustainable aviation. However, because the production of sustainable aviation fuel, SAFs, is quite low at the moment, we need to have policy-driven impact that would increase our sustainability, and we need to increase our SAF production to achieve those sustainability goals. In the dire need of combating climate change, we also there is a need for revolutionary aircraft design, in which we have to go through various new airframes and other aeroplane designs. But alternative propulsion technology, such as using electric power or hydrogen power, is also one of the steps to move forward. So if we can recapitulate the goals that we want to achieve in the process for achieving sustainable aviation, we need better fuel-air mixing, we need lower emissions, and we also need fuel flexibility. So going from the things that we need and the things that we want to achieve, if we come back to our fundamentals, we need better fuel-air mixing. So one of the concepts of fluid mechanics that remains very fascinating and remains very curiosity-driven research is jet in cross-flow configuration. So this configuration is basically where we have a jet which is injected in a cross-flow, and that results in a very complex fluid mechanics configuration that results in shear layer vortices, counter rotating vortex pair, horseshoe vortices, and wake vortices. Amidst of all presence of all these vertical structures that is controlled by jet to cross flow momentum ratio, it results in many fluid mechanics driven phenomena, including entrainment. Entrainment where the cross flow is getting entrained by the jet itself. So if you look here on the image on the right side, we see that the green all the way up to orange markers of the vectors are coming into the contact of the jet, and it is getting entrained by the jet itself. So what does it give us? It gives us a mechanism to enhance mixing of fuel-air mixing. Based on that concept, we are going to look into more in spray-initiated cross-flow. I know that I have promised a linear azimuthal flame combustor concept, but let's take a moment at the fundamentals of that first. So the spray-initiated cross-flow, the experiments were conducted where we have two flame configuration, where there is a first stage flame, which is basically created by 4x4 array of methane, hydrogen, air premix flame up to 50 kilowatt and equivalence ratio of 0.5. And in the second stage, we have kerosene flame, where the kerosene is created using an air blast spray. And the spray characteristic is changed and modulated by liquid air to liquid mass flow ratio, ALR, between 2 and 6. So if we look at two operating conditions here at a fixed 5 kilowatt, we see that if we have a jet momentum ratio described based on the kerosene jet itself, it is 61, and the ALR, the air to liquid ratio of the atomizer, is 13.8 microns. And when we increase the ALR to 6, the jet to cross flow momentum ratio increases while decreasing the mean diameter of the spray. So I want you to focus on this. So when ALR is low, the jet to cross flow momentum ratio is lower. So we can infer that there would be low mixing, but the SMD is higher, which means the time scale for evaporation would be higher. On the contrary, when we have higher ALR, we have high jet to momentum ratio, more mixing. And then when we have lower SMD, which means low size droplets, leading to faster evaporation. Now, keeping these two things in mind when we move forward and do experiments with several diagnostics, including OH chemiluminescence as well as OH PLIF. So the OH PLIF setup is shown over here. We see that we have a dye laser that was illuminating the kerosene flame itself at multiple height locations, and to see what kind of OH field it is creating, we also placed excitation camera to look at laser profile at the inlet and absorption camera to look at the laser profile at the outlet. So first things first, when we see the OH chemiluminescence, which gives a line of sight integration and overall OH intensity of the flame, we see that for low ALRs, the flame centroid is mostly on the windward side. So it is over here where the red cross marker is. When we have a high ALRs, the flame is penetrating more into the cross flow, and the flame location is changing to the leeward side, which means changing the ALR, changing the jet to cross flow momentum ratio, changing the Sauter mean diameter of these flames, we can control the flame characteristics and flame locations. Looking at the flame topology and fluid distribution through PLIF measurements, we also see similar results. However, we get extra information when we look at the fuel clusters. So for ALR, we look at a lot of droplets, which are unburned fuels, whereas for high ALRs, the intensities coming from the unburned fuel are very localized and concentrated near the location of the fuel injection. So again, going back to the basics, which is when you have higher jet to cross flow momentum ratio, there is going to be better mixing, which also simultaneously results to lower droplet sizes, leading to better evaporation. We also looked at the reaction fronts by correlating the profile, the image profile, and between the excitation camera and absorption camera for the PLIF studies. And we see that for ALR2, the reaction fronts are very thick. Again, inferring that it is diffusion-dominated flames. On the other hand, when we have ALR6, we see that the reaction fronts are getting thinner, and as we go up in height, they become more inferring something like a gaseous flame, and which results that it is burning more efficiently when we have ALR6. So we needed to know from the experiments what kind of flame fronts we are having. We conducted some large eddy simulations in collaboration with India Justi, Imperial College London, and the boundary conditions were extracted from the PLIF measurements and temperature measurements done in experiments and put in the large eddy simulation boundary conditions. And here, what we saw that the OH profile is very similar what we see in the experiments, as well as the location of the reaction fronts. So we see that again here for the ALR2, we see the OH profile is mostly dominated on the windward side. And when we have ALR6, the OH concentration is dominated on the leeward side. And similarly, for the unburned fuel ratio, it replicates what we saw in the PLIF results of the spray and cross flow. Now, the mixing mechanism. For isolating the mixing mechanism, we looked closely at the vorticity dynamics of the jet with the velocity fields. So if we look at if the vorticity field for ALR2, you see that the pockets of dominant vorticities are on the windward side. The bottom figure gives you that. And when we look at ALR6, the vorticity field is mostly on the leeward side. High vorticity in ALR6 on both sides. So it can be inferred that when we have ALR2, there is shear layer mixing, although very one-sided. And when we have ALR6, there is shear layer mixing, yes, but we also have entrainment-induced mixing. In total, it represents that when we are changing the ALR, it is changing the jet to cross flow momentum ratio, and that affects the mixing hydrodynamics in both configurations. Coming to the droplet dynamics. Now, there are two things that should be considered in droplet dynamics. The first is how fast the droplet evaporates in the cross section and how fast it gets transported with the cross flow. To do that, we calculated the burning time scale of the spray using the SMD values, and we also calculated the convective time scale of the cross flow that is given by the cross-sectional length of the channel and the cross-flow velocity. So if we look at the comparison of these two timescales, we see that for ALR2, it is greater than 1. And for ALR6, it is less than 1. So essentially what it is telling us, the timescales again are coupled with respect to convection. So for ALR2, the spray time, the evaporation time scales are higher. So it takes a lot of time for the spray to get evaporated and burnt in the process. But when we have ALR6, this time scale is lower. So there is faster evaporation and better mixing with the crossflow. So this is coming to the spray initiated crossflow study. This is what we have to keep in mind, that there is inherent coupling between the spray characteristics coming from the air to liquid ratio variation and the jet to crossflow momentum ratio variations. So if we have low ALR, there will be smaller jet penetration, but larger droplet sizes. So it only leads to shear layer mixing while the droplet evaporation timescales are larger. So combination of both results in inefficient mixing, and that leads to unburned fuel at the exhaust. So when we have higher ALR, there would be high jet penetration and smaller droplet sizes, resulting in both shear layer and entrainment-induced mixing in the flow field. And the smaller droplet size distribution would lead to better, faster evaporation of droplets, leaving better efficient mixing and relatively low unburned fuel at the exhaust. So fundamentally, if we understand the spray-initiated crossflow, we can combine these studies to scale it up for the leaf burner and understand more the leaf concept itself. So as promised, coming to the leaf combustor itself, the leaf lean azimuthal flame combustor concept was initially introduced and developed and patented by Professor Masarakis and team at University of Cambridge. And in the joint effort under the Horizon 2020 Lifinox project, which was in collaboration with University of Cambridge, Imperial College London, University of Napoli, and ETH Zurich, a new leaf design was developed at ETH Zurich, incorporating several geometrical modifications, including air-assisted mode of spray atomization. And at ETH, we also demonstrated that there is a dual fuel jet A1 and hydrogen capability of the burner. Moving into the leaf combustor concept itself, so starting with the combustor design, so the combustor has a top air manifold that comprises of 12 top air injectors that are angled at 45 degrees, and there is a bottom fuel manifold that houses 3 air-assisted Delavan air blast atomizers and 3 gaseous inlet ports, and also the igniter. And the cross-section of the leaf combustor is hexagonal in shape. And moving forward, if we look at the leaf concept, the concept resides in the injection of sprays from the bottom fuel manifold in the presence of top air angled injection that leads to a spray initiated crossflow. So going back to the first thing that we learned is spray initiated crossflow thought process, that the combustion products of one spray is going to ignite sequentially and continuously the next spray, and that leads to soot-free and low NOx Jet A1 combustion. The diagnostics for the leaf and its operability was conducted using OH chemiluminescence in the chamber, as well as laser diagnostics of spray knee scattering and OH pliff at central plane, at the dome, as we call it, and the injector plane, that is LS2. The operating conditions to check the operability limits in the leaf was conducted at several thermal power of Jet A1 that varied from 15 kilowatt to 25 kilowatt, and ALR ratios, the air to liquid ratio of the atomizer, from 2 to 4. The global equivalence ratio was kept constant across all the operating conditions at lean conditions, 0.7 approximately. So let's look at what happens at ALR 4, the flame topology. mostly for all the power values remains leaf, which means it is a beautifully rotating flame where one spray combustion products are igniting the next one. So essentially, the fresh reactants are getting diluted by the products of the previous spray combustion. And when we look at inside the chamber at LS1, that is the central plane, we look at the spray me scattering, we see that there is barely any intensity over there. When we look at LS2, we see that there is a bit of intensity near the injection point, which is fairly normal given that the spray is still breaking up, the spray is still dense at the injection point. Now, there is a little bit of interesting event when we go from ALR4 to ALR2 in transition. So I'll let you watch this video for a few seconds. The flame transitions. So initially at ALR4, the flame was in leaf mode where it was rotating and one spray was igniting the following spray. But as soon as there is a transition where the ALR of the atomizer is changed from 4 to 2, the flame becomes a bit unstable. To investigate how that is happening, we looked again at the flame topology at ALR2 with OH chemiluminescence, and you see it is a tubular flame with mostly stabilized at the dome of the BFM. And when we look at the spray me scattering at the central plane, sorry, this should be 2 over here, my apologies. At the central plane, we see that there is a lot of intensity of droplets around the tubular flame, suggesting unburned fuel. And when we look at the injection plane, we see again unburned fuel intensities. So if we go back to again the basics of spray in cross flow, we know that the spray flame is highly affected by the droplet size distribution, function of air to liquid ratio, and the entrainment induced mixing. So the first thought process for us is to go into the details of the spray droplet size distribution and look how that is getting changed when we have air to liquid ratio variations. So this is a famous correlation of risk and Lefebvre for spray Sauter mean diameter, which shows that how the Sauter mean diameter is a function of liquid properties and air to liquid ratio. Using this, we created the Rosen-Ramler droplet size distribution for the operating conditions of the leaf combustor for different jet A1 powers. So if you see, this is the size distribution for ALR4 and this is for ALR2. So size distribution of ALR2 is of course higher than the ALR4 where the SMD is close to 20 micron, whereas for ALR2 it is getting on a bit higher side. We have the droplet size. Now we want to look at what is the characteristic length scale and time scale that governs the combustor. So first things first, as I said in a couple of slides ago, that the whole concept relies on the fact that the combustion products of one spray is necessary to provide vitiation to the next spray. So it has to get evaporated, mixed, and combust properly to produce enough good environment so the next spray could be ignited and continuously burned. So for us, the characteristic length scale would be the convection length between the two atomizers. And the time scale is divided by the velocity, the tangential velocity between these two. So this time scale signifies how much time the convection would take place to transport the hot products from one atomizer to the next atomizer. And the second characteristic length scale would be our maximum droplet size. So which essentially governs the fact what is the minimum size, what is the maximum size that would be evaporated between these two atomizers. So if we calculate that, and if we see for ALR4 that convection value of diameter that would be evaporated between the two atomizers is basically around 90% of the initial spray distribution, which means when we are operating at ALR4, all of the spray, essentially 90%, would be evaporated between the two atomizers. But when we have ALR2, the respective convective diameter is only 20%. So between the two atomizers, not all of the evaporation would take place. Hence, it shows that this instability is being governed, or it is coming into the picture because there is not enough evaporation and mixing of the evaporated liquid fuel. So even that thought process in mind, we also develop a predictive non-dimensional time scale that is a function of the convection and spray evaporation. So the non-dimensional time scale was formulated in terms of the ratio of evaporation time scale of the spray and convection time scale of the burner between the two atomizers. And we see that this ratio remains higher than 1 for ALR2 and lower for ALR4, suggesting that for ALR2, there is inadequate spray evaporation compared to convection in the field, and whereas for ALR4, a considerable amount of spray is being evaporated between the two atomizers. So if we try to recapitulate the topological transitions of jet A1 leaf, we see that the characteristics is highly dependent on the variation of ALR, again, spray characteristics, and the governing time scale is dependent on the convection and spray evaporation itself. And going back to the basics of spray and cross flow, we can draw a lot of analogies and say that for ALR4, because of the smaller droplet size distribution and better mixing, we have a stable leaf operation, whereas for ALR2, larger droplet size leads to a tubular topology, essentially an unstable configuration. So what do we do when we have unstable liquid flame? We inject hydrogen. So this is the part where we decided that hydrogen would make a good candidate to inject into the burner to stabilize and maintain the leaf configuration. So on the left-hand side, we see here the tubular topology without the hydrogen injection, and then full leaf configuration with hydrogen injection. Again, for ALR4, we did the same. The leaf didn't change, but we also needed to investigate how does the hydrogen injection results any change in emission characteristics. So here again, our OH chemiluminescence signature for ALR2 at 15 kilowatt and soot luminosity at 15 kilowatt. So you see there is a bit of soot variation inside the burner, which is because, of course, for ALR2, the droplet size are larger. Next, when we look at the chemiluminescence of ALR4 at 15 kilowatt, it is again a nice rotating leaf configuration. And here is the soot luminescence. I am playing the video, but we don't see any soot in there, which suggests that there is highly efficient and given high mixing characteristics of the ALR4 and the resulting flow field results in less soot at the exhaust and inside the chamber. The exhaust measurements for both NOx and soot emissions were performed for hydrogen-assisted leaf, and we see there with increasing the ALR, the NO emissions are increasingly lower, coming back to single digit as low as 8 ppm VT, whereas the O2, the excess oxygen at the exhaust remains well below 4%, suggesting complete combustion of the fuel inside. We also did some soot measurements, scanning mobility particle sizes with the support of Adana and Gianluigi from University of Napoli. And we see that the soot are barely there. Anything less than 100 nanometers is these volume fractions are very low. Just for a comparison, if we compare it to a non-leaf, non-suiting, if we compare it with a suiting condition, this is what it should look like. So this is a condition, operating condition where there is a soot formation, and all of these conditions are without the soot formation, which suggests that the leaf with hydrogen-assisted combustion still produces ultra-low NOx and soot-free combustion. With the hydrogen-assisted leaf, it was conferred that H2 addition does extend the operating condition even at low ALRs, which is good for the aviation applications, given that high ALRs we do come across higher pressure drop. And exhaust measurements report that even with hydrogen-assisted combustion, we have a low level of NO and absence of soot in all the operating conditions. Given that we saw liquid fuel operations with the leaf and hydrogen-assisted, we tried to take it to the full hydrogen operation. So here is a video that I'm going to run that will demonstrate the dual fuel capability of the leaf concept. Where at the bottom figure, you see that in real time, the black line is the kerosene power and the blue line is the hydrogen power. And in operation, we were changing the both. So we are putting the kerosene power down and increasing simultaneously the hydrogen power. And this is the moment where the hydrogen power becomes higher than the kerosene power. And we were able to achieve full hydrogen leaf operations. The flame is barely visible given hydrogen's luminosity, but moving forward. So in the hydrogen leaf operations, as initially told about the leaf configuration itself, the hydrogen was injected including using these three gaseous ports from the bottom fuel manifold. And the operating conditions were changed by changing the top air flow rate and the bottom air flow rate. Now here, the other thing is also necessary because we are operating with hydrogen. We also need to conduct experiments to look at the premixedness on the system. So we introduce a new parameter here called air ratio. That is the ratio between the bottom fuel manifold, the air injected from the bottom fuel manifold, in comparison to the air from the top and the bottom. So this ratio was varied between 0 to 1, where 0 is air only from the top and 1 air only from the bottom fuel manifolds, essentially leading to a premixed hydrogen jet flame. The OH PLIF measurements for the hydrogen leaf are very interesting. So if we look when the air ratio is 0, this is essentially a diffusion-dominated flame. But as soon as we start increasing the air injection from the bottom, we see some sharp reaction fields coming through. And when we go to AR as high as 0.5, we have a different flame characteristics where we have a jet flame at the bottom and we have another flame front at the top. So for the first time, we saw that there is a dual flame structure in the combustion chamber when we are operating with hydrogen. One is the premixed jet that is coming because there is also air injection with the hydrogen flame, hydrogen itself, and there is a top diffusion flame when the reaction products, unburnt hydrogen, gets mixed with the fresh air from the top. There is a local diffusion dominated flame over there. Several large eddy simulations were performed here by the ABBP code, and the more details about this can be found in one of our Proceedings of the Combustion Institute paper on the methodology of it. But essentially, the LEAF LES was utilized to see what is the temperature distribution in the combustion chamber and what is the mixing characteristics of the hydrogen flame and flow in the chamber, and how does that affect the NO formation in the chamber. So first things first, the LES was conducted for AR ratio 0.5, and we see that it is quite close to what we see in the experiments at power 10 kilowatt. Similarly, when we have AR ratio of 2.5, again, we have similar characteristics of LES as we see in the experiments. AR ratio of 0 was not done using the ABBP code due to inherent complications arising from the code. The NO emissions, if we look at from the left to right as a function of AR ratio for different powers and different global equivalence ratio, we see that there is a trend of decreasing or reduction in the NO. And that was quite similar across all global equivalence ratio, starting from 0.75 to 1. One thing that is peculiar to notice in 0.75, of course, also across all global equivalence ratio, is the NO concentration. The NO concentration decreases when we increase the AR ratio. So when we are coming from 0 to 0.5, it decreases, and 0.5 onwards, it starts to increase a little bit. LES are described here with the black cross marked, and we see that LES is coming quite close to the experiments observations. The flame structure using the LES was retrieved and was identified using the Takano index, and we see that for AR ratio 0.25, most of the flame is diffusion dominated. And when we have AR ratio of 0.75, it is premixed flame dominated. This helps us to retrieve also to look at the temperature, and we see how that affects the NO formation. These are some of the NOx chemistry that was retrieved from the LES. And one thing that is here, without going into the details of different pathways, it is important to notice that in the chamber, most of the NO formation is happening near the bottom fuel manifold, when the Z coordinates is closer to 12 millimeters, which is very near to bottom fuel manifold. And this remains consistent all across board. And this is happening because the temperatures are higher, closer to the bottom fuel manifold where the fuel is getting injected. Coming to the NOx formation pathways for the hydrogen flames, the famous thermal pathway is the Zeldovich mechanism, where N2 and O combine to form NO. And there is another route that becomes dominant, if you will, that is the NNH route, which forms closely, mostly in the premixed flame structures. And if we look at these formations, we see that when we have higher temperature regions, the NO formation is higher, of course, going through the Zeldovich mechanism. And when we increase the AR, this temperature distribution gets reduced, which means the thermal pathway is getting a little bit less active. However, when we look at the NNH route, we see that the NNH route becomes dominant when the AR ratio is increasing, suggesting that NNH route is dominant in the premixed region over here. It seems that for the leaf operations with hydrogen, we have to play around with the AR ratio, the ratio between the bottom air and the top air, to achieve a sweet spot where the thermal pathway is not that dominant, and also the NNH route is not that dominant. And cumulatively, that results in lower NOx sweet point. So overall, with the hydrogen leaf, for the first time, we characterized and identified a dual flame structure. The LES, as I said before, indicated the AR significantly affects the mixing characteristics and the temperature distribution within the chamber. For higher NO emissions are mostly in the diffusion-dominated regimes due to NO formation in coming through the thermal pathway, and combining the thought process of the NO formation from higher temperature, as well as restricting the formation in secondary pathways like NNH route, there seems to be an optimum air ratio close to 0.5 that results in lower NO overall. So currently, we are working on Jet A1 to leaf Jet A1 to hydrogen leaf transitions, which is essentially the first video that I showed, where we are increasing the power of hydrogen and decreasing the power of kerosene at the same time. So these are very recent results, and we are still in process of analyzing and understanding them. But what I want to show here, that the leaf concept works very well, and we tend to have stable operations for the jet fuel and hydrogen fuel. But one thing we must consider when we have hydrogen leaf is the instabilities. So if we look at the full jet fuel operations, we see again nice rotating chemiluminescence in the chamber. And when we have hydrogen in itself, chemiluminescence is a little bit less dim given hydrogen's luminosity, but we do see it. But if you look at the pressure, PDF, in the chamber, as we increase the power, PR1 means power ratio 1 means only hydrogen operation, and we see that the pressure in the chamber is having a bimodal configuration, which seems possibly when we have hydrogen in the system, there is going to be different temperature distribution as we saw before, and that will also lead to different hydrodynamic instabilities as well as thermoacoustic instabilities. And these are just conjecture as of now, but we are moving forward to understanding them. Again, here same hydrogen to leaf transition. One thing about the leaf, and I guess I will elaborate more on that if there are any questions, the leaf is modular in its design. So the chamber length can also be varied. So till now, we presented the results of a fixed chamber length. But if we start modulating the chamber length, there are new instabilities that are also coming into the picture, where even a stable liquid leaf tends to show topological transition like one shown in the video. And this seems to be an effect of how the mixing characteristics is getting altered when we reduce the length of the chamber. These things are also in process, and we are trying to learn more and more day by day. These are the pressure points for different leaf operations in transient conditions. So you see when you have a leaf that is still in leaf mode, the pressure is quite high, and then when we lose it to a tubular flame, the pressure intensities are lower and they are getting back up again. So it's behaving like a cyclic occurrence, and we need to investigate more what time scales or what length scales are controlling these behaviors. So overall, The concluding remarks for the leaf concept is basically when we are having a very highly turbulent environment generated by continuous mixing of reactants and products, it leads to ultra low NOx and soot-free combustion, both for kerosene and hydrogen. For Jet A1 leaf, the change in reaction front location and morphology, controlled by air to liquid mass ratios, flow ratios, becomes an interplay between the mixing and the spray characteristics that results in a very strong interdependency of spatio-temporal scales of where the length scale is the length scale between the two atomizers, and the time scale is the convective time scale and the spray evaporation time scales. Hydrogen seems to be a viable candidate for maintaining liquid leaf stability while also maintaining low NOx at the exhaust. Leaf concept also works in transient and for dual fuel flexibility as well as full hydrogen capabilities, where for full hydrogen, the exhaust emissions can be controlled by changing the air ratios from the top air manifold and the bottom air manifold. The investigation pertaining to transient leaf are still in progress, and I would be very happy to come back to them on a later date and time. I would like to acknowledge the funding received from the Clean Sky and European Commission under the Lifinox project and the Research Innovation Scotland between the collaboration from University of Edinburgh and ETH Zurich, CAPS Lab, Professor Nicola Noire and Dr. Chetan Vegar. I would also like to take this opportunity to talk about my research group at the University of Edinburgh. So we are Experimental Multiphysics and Multi-Phase Flow Group, the EMP Squared group. And our research is mostly in three directions. One is transport phenomena in multi-phase flows for emission control, which we have received a new investigator award for that. Second is fuel trajectory control using electrostatic fields. It is being conducted from the ERP seed funds, and essentially we work on modulating liquid fuel trajectory using electrostatic atomization and external fields. And the third is the dual fuel combustion of hydrogen and liquid fuels for power and propulsion. I will give you a bit of teaser of the external electric fields here. The idea is to again come back to the basics, to utilize external forces to achieve precise fuel-air mixing. So currently, me and my PhD student, in collaboration with Dr. James O'Shea from Department of Physics and University of Nottingham, we are trying to develop this experimental setup where we inject charged droplets in the presence of electrostatic field, and we see how that controls the trajectory of the droplets. And that would, with the idea that if we can control the droplets in a crossflow, we can essentially have modulation of how much fuel and air could be mixed without losing the droplet in a convective field. And that's all from my side. So many thanks for your attention, and I'm happy to take any questions.
Thank you. Thank you, Khushboo. Thank you very much for this very interesting talk. Now it's, we have some time for questions. So I will ask if someone from the audience has any questions, please feel free to unmute yourself and ask.
Maybe I start so that people
break the ice.
Yeah,
Alessandro, sure.
The icebreaker. So I was wondering, so you showed all these parameters that are important to check in cross flow to have effective mixing and have this behavior that you expect from the leaf.
Yeah.
I was wondering how these parameters change, for instance, with the addition of hydrogen, or how they would affect the optimality of these parameters.
Yeah, so I mean, for the spray and cross flow, the parameter that was, or the leaf itself with the topology, the parameters were spray itself and jet to cross flow momentum ratio. So if we inject hydrogen that at low power, of course, this essentially does not change any of those two, but it changes the temperature field around the sprays.
Indeed. Yeah, that's
so
what I,
that affects and that's how we can stabilize it, because it is giving that hot environment for the spray to be evaporated. So that is a good thought process, essentially. So when we are calculating the evaporation time scale of sprays, perhaps we can put a modified temperature field or temperature parameter that can account for that change. Does that answer your question?
Yes, yes.
Yeah.
I mean, I was just curious. But anyway, thanks. Thank you very much.
Okay, I have a question regarding because you talked about the flame structure when you for the hydrogen flame. What are the flame structures that you see in the kerosene spray and
Okay, so
flame
for
structure?
this for the spray in cross flow, we do see that if we do the pliff of individual sprays, right? So we do see that when we have ALR2, which means when there are larger droplet sizes, we see very thick reaction fronts, which is very diffusion dominated. But when we go at higher ALRs, that is ALR6, we start seeing these thin, reaction fronts. For the leaf itself, when we did the OH pliff, and there are 6 windows in the combustor, so it was very hard to do a calibrated pliff where we can correlate OH to the intensity, because we still have to do diagnostics configurations to achieve the both. In spray and cross flow, it was quite easy. But I presume for ALR6, we could still see those thin flame fronts, and even with the hydrogen assisted leaf as well, those reaction fronts would be thinner, if you will, and will resemble to something that we might see in a mild combustion regime. But for ALR2, because we have those big droplets they have very high intensities in fuel lift, it would be difficult to comment whether those are in mild conditions. It would be more mixing dominated, yes, but it is hard to comment on what regimes they are burning in. Does that
Yeah,
answer
yeah,
your
yeah,
question?
yeah. No, absolutely. And thank you. And I was thinking, if you have now 6 quartz, 6 optical lasers, 6 quartz windows. How did you manage with the heat loss?
Yeah, so these are actually 12 windows. So each side are 2 windows. So one is inside, one is outside, and in between the two, there is an air cooling flame. Sorry, there is an air cooling flow. So technically, all the windows are cooled all the time. When the LES was done, this cooling was taken into account to account for the heat losses. Using their conjugate heat transfer.
Wow.
Yes. So for the LES, it was accounted for. For the experiments, we didn't go into the details of how the flame is losing heat. So it was never, part of the investigation. But when the burner was designed with the external consultancy, it was deemed necessary to put that airflow cooling there.
Okay. Interesting. Okay, if I don't see any question from the audience, so I would like to thank the speaker again for the very interesting presentation. And thanks again, Khushboo, for accepting our invitation. And hope to see you everyone at the next appointment of the 40 under 40. Thank you. Thank you very much. Khushboo, have a good day. Have a nice weekend.
Thank you, everyone. Thank you for having me, and have a good weekend as well.